linear systems refers to, well, we'll show it a couple different ways, but it refers to two lines that are crossing each other, okay? So this is our coordinate grid, a little graphical representation. We have our x and our y, and all it's talking about is if we have one line and then we have another line, the question's asking, how do I calculate what this point is? What is the x and the y value? So graphically, I could try looking at it, and if I take a look here, assuming that each of these is a unit, I didn't make this very nicely, I could do a little estimating. This looks like it's about 1 in terms of the x value, and then this looks like, oh man, that's like 1, maybe 2. I didn't draw that on a good space, but let's say we estimate, okay? Estimate, it's at 1 and 2. That works out nice. But if we want to get a very exact answer, we'll want to do algebraically figure out where they intersect each other. So there's a couple different methods you can use to algebraically solve this. First of all, you need the equations of each of the lines, okay? Now, this is just an example. What I'm going to do is I'm going to go to a new page. I'm going to make up an algebraic expression, and then we'll test it to see if we can find it graphically after. So let's say I have a question like this. Y is equal to 2x plus 3. That's one of the lines. And then I have another line. Y is equal to negative 3x minus 2, okay? These both represent one line. I could go about graphing it, which I will quickly do down here on the right. Okay, that was not a good spot. Let's try to use these lines as best as we can. Here's our x and our y. So let's graph our first one. We know our general equation to be y is equal to mx plus b. I'll use colors to represent these here. So b is in green, y. M is in blue. This is our y-intercept. So we count up 3. 1, 2, 3. We have our y-intercept. And then we need slope. We know we can turn that into a fraction. We just learned it. And it's positive, so we go up 2, 1, 2, and over 1. And then we do the reverse. 1, 2, down 1. So it looks like we have a line something like that. Okay? We'll do the exact same thing with the other one. This one has, negative 2. So our y-intercept is negative 2. We go down 2 and plot our point. And then what's our slope? We turn it into a fraction. It's negative 3 over 1. So we go down 3. 1, 2, 3, and over 1. And then we do the opposite. Up 3. 1, 2, 3, into the left 1. Oh, this one looks like it's going to work out really nicely. I didn't anticipate that. Usually when I just make questions off the top of my head, we don't get really nice points of intersection between them. So this point of intersection here, okay, looks at negative 1 and positive 1. So it is negative 1 and positive. Looks good graphically. We should probably confirm algebraically though. So algebraically what we can do is we have two equations and we can substitute is a very common version. There's another one called elimination, but we'll do substitution because it's the one that's used usually most frequently in high school after grade 9, 10, and 11. So what we have here is two statements. One statement says y is equal to this equation, 2x plus 3. Another statement says y is also equal to this equation. So in other words, what this is saying is y is equal to both of these. Both of these things are equal to each other. So what we can do is I'm going to take equation 1, and I'm going to write out y is equal to 2x plus 3. Well, for substitution, what I'm going to do then is I'm going to say, since this is y over here, these are both representative of y, my equation 2 states that y is equal to this. So I'm actually going to take this value and substitute or replace the y in this equation with all of these numbers. Okay? What that will do is get rid of our y's and we'll only have an x, and then we'll be able to solve for x. So our next step here is we'll go negative 3x minus 2. So that's what we just substituted in. We took that and replaced the y, is equal to 2x plus 3.
And we gather like terms.
That's exactly it. We gather like terms. Have you done this before?
Yes, I think we did learn.
Ah, okay, good. So then we'll just quickly go over it. From this point, we want to get maybe variables on the same side. Since this one is a negative variable, I like working with the positive stuff. I'm going to move that over, and I'm going to put our constants to the other side. I'll do it all in one step. So we'll have the 2x, we'll say, and then this negative 3 will become positive 3. And in this case, we'll have negative 2 and technically negative 3. Okay? So we're going to end up with 5x, and this will be negative 5. I divide both sides by 5 because 5 is the coefficient here. x is equal to -1, which is exactly what we found graphically. Great. Our next step is we're going to substitute back in. Same idea, we use substitution. I can substitute to either equation. So to prove that, we'll bring over equation 1 again. Y is equal to 2x plus 3. And equation 2, y is equal to -3x minus 2. We had just found that x is equal to -1, which means I can replace the x in both these equations with -1, and I should, assuming this is correct, I should get the exact same y value.
Y should equal +1.
That's exactly it. Y should equal +1, assuming that graph we drew above was correct. So we'll try to carry this out. Y is equal to 2 times -1 plus 3. Y equals -2 plus 3. Y equals
And
1.
when you know it's +1.
There you go. Same concept here. -3 times -1 minus 2. Y equals 3. Yep. Y equals 1. And boom, we got it. So we've just shown, using two different methods, we've shown graphically the answer to this linear system, which is -1, +1. We show that's graphically. And we've also gone about it algebraically. We've solved that. Another version of this is potentially you can make a table and try to find where the coordinates are the same. The problem with that is linear equations are continuous, which means you don't always get a nice number, and that means it might be really hard using a table to solve. That's why it's not commonly taught, but tables are another way to represent mathematics. So I'm going to quickly make a table here. Actually, you know what I'll do? I'll use some technology to help us out a bit with it. We got some decimals here. We were doing inequalities before. Let's bring up the two equations. So first equation was y is equal to 2x plus 3. I'm going to turn it into a table. Okay. Our second equation was y was equal to -3x minus 2. And I'm also going to turn that into a table. So if I take a look here, there's a really special coordinate. -1 and 1, -1 and 1 happens to be the same. The rest of the coordinates, -2, -1, -2, +4, they don't match. So you're essentially looking for a matching coordinate. If it doesn't have a whole number answer, tables are very inefficient because you're essentially trial and error and guessing your way through it. Luckily, this has a whole number answer, so it worked out for us. It's another way to represent mathematics, but not wildly efficient for solving linear systems. Okay, so let's stop it.